So in single variable calculus, you did integrals. Now you're in multivariable calculus, you're going to be doing multiple integrals. So this one is 2D integration, and so we're going to start off with a little example, intuitively what it means, and a nice way to compute it. All right, so multiple integrals. So you have this integral, its bounds are 0 to 1. Then you have another integral right after it, its bounds are 0 to 1. We're integrating this function, z equals x times y, so it's some height, and the height is determined by the x-coordinate and the y-coordinate. That'll tell you how far to go up in z at that point. And then you have dy dx. In the order here, you do have to keep track, right? So this integral, the interior one, like parentheses, the dy goes with 0 to 1. So y is being integrated from 0 to 1. And then x goes with the outer integral, and that's from 0 to 1. So what you're doing is you're integrating this function z equals xy to find its volume on a square that's 1 by 1, and right, one of the corners is 0, 0, 1, 0, 0, 1, and 1, 1. It's this unit square in the first quadrant in the xy plane. All right, and then this function xy we're integrating. So I tried to draw it here. I'm not the best artist. But here we go. When y is 0, that means you're on the x-axis. Then z equals x times 0, so it's actually the z height is 0 on the x-axis. If you're on the y-axis, that means x is 0, so then you end up with 0 times y, so that ends up being 0. So z also has a value of 0 on the y-axis. And then if you're at x is 1, y is 1, then z equals 1 times 1, you get a height of 1. If you're at x is equal to 1, so this plane here on this side, then you end up with z equals 1 times y. So you actually have z equals y in the yz plane right here. And then if you're on if you're at y is equal to 1, so this back plane on the back, this triangle, then you're going to end up with x times 1 equals z. So you'll actually get a slope of positive x on the back here, going from this point here up to there. It's a straight line. All right, and then in between, it's kind of like you took a net almost, and you put you tethered points here, 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 and here for the four corners, then you kind of let it drop down. That's kind of what it looks like. All right, and so the double integral here is we're finding the volume with its base, this rectangle on the bottom, and its height is defined as this function z equals x times y. All right, going back to your Riemann sums, right, this is equal to, it's the limit as m comma n go to infinity, where n is going to go with x and m is going to go with y. And you're doing I equals 1 to n, j equals 1 to n, of x times I times x sub I times y sub j times delta y times delta x. So I didn't draw all the rectangles here, and I didn't do a great job, but essentially the delta x, if you're dividing this up, in this case n and m are both 4, so you're dividing it up into 4 little segments, but you end up with this grid rather than just a bunch of little segments along the x-axis. So in here, we're using, like, this is x1, y1, this is x2, y2, this is x3, y3, this is x4, y4. And so you'd want to draw more boxes, but I didn't. But right, we're essentially summing up a bunch of little rectangular prisms, and that'll approximate this area. Not very well, because it's only 4 by 4. That's the idea. But from here, we can define what x sub I and y sub j are, and also what delta y and delta x are. All right, so let's start. So delta x is equal to, all right, so I'm going from 0 to 1, and I have n divisions. So if I do that, 0 to 1, n divisions, that means each of these lengths is 1 over n. Right, I have n of these, 0 to 1. Each division delta x is 1 over n. And similarly, delta y, we're going from 0 to 1. There are m divisions for y in the y direction, and so that's going to mean delta y is 1 over m, right? Because 1 is the length from 0 to 1, and there are n divisions. So this is 1 over m. All right, Then x sub I, y sub j. So x sub I. Well, when x is equal to, when I is equal to 1, we're here. When I is equal to 2, we're here. When I is equal to 3, we're here. When I is equal to 4, we're here for n equals 4. So it's really, we're just going, 1 delta x each time. And so it ends up being I times delta x. Which is just I over n. All right, and you'll find similarly y sub j. Well, that's j times delta y. That ends up being j over m. All right, so we can actually write the summation out and replace it with i's and j's and m and n's. So that's the same as, sure, I'll put the limit in. Close enough. All right, so m comma n go to infinity. Summation I equals 1 to n, j equals 1 to m. And then we have x, so it's x sub I, so it's I over n. Then we have y sub j, which is j over m. Then we have times delta, where did I put? Delta y, so 1 over m, 1 over m. All right, and it turns out we're going to use a little formula from way back when. If you have 1 plus 2 plus 3 plus dot 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 plus n, there's a formula for that. It ends up equaling n times n plus 1 over 2. All right, way back when, you might remember that thing. And so in here, we can actually do that for each one. So we can simplify the j first if we want, because every single I sub n, like I equals 1, it's still going to do the whole sum for the j's. For I equals 2, it does the whole sum for the j's. For I equals 3, it does the whole sum for the j's. So we can actually just put that out. So I'm going to simplify this a little. I'm going to have a 1 over m squared n squared in the front. So 1 over, and I should put that before the limit. I've got m comma n go to infinity. I have 1 over m squared n squared. I'm going to have sum. I'm going to have my I equals 1 to n. And I have my I here. But that's multiplying the summation I'm going to be doing for j on the inside. But I already know what that is, because it's 1 plus 2 plus 3 plus 4 plus dot 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 plus m. All right? So that's going to end up equaling, where'd it go? So I'm going to replace n with m here. So it's m times n plus 1 over 2. So I've actually completed the first summation with the j's. And then it ends up being the same thing for I. I just have I by itself now, so it's the limit as m comma n go to infinity of, where'd it go? 1 over m squared n squared. And I've got, I'll do the I piece now, so it's going to be n times n plus 1 over 2. And then I've got m times m plus 1 over 2. Now this filing cabinet gets in the way. But now if we simplify that, we end up with, I have to squeeze this in. So limit as m and n go to infinity. So it's n squared plus n times m squared plus m all over n squared times m squared. Oh, and I forgot my 1/4. Excuse me. Let me put the 1/4 out here. But if we take the limit, only the highest power terms matter. So it's really this n squared and this m squared, because as n goes to infinity, n over n squared goes to 0. So that whole thing actually ends up being 1/4 times 1. So according to this Riemann summation, that's what the integral is supposed to be. And we can actually just do the integral. So you don't, hopefully your professor, lecturer doesn't make you do that very much. But wow, this is going to be a lot easier. So you might think, well, okay, double integrals, it sounds like it's going to be way, way more difficult than single integrals. The integration part of the integral isn't really much more difficult than single integration. You just do one single integration and then you do another. So for that, we're going to evaluate the first integral. So we're going to take the integral. So we're going to have integral 0 to 1. I'm going to still have my dx on the end. I'm going to integrate the y term. So I have x times, and I'll put here y squared over 2. And this is evaluated from 0 to 1 dx. Okay, so that's the result of the first integral, and then I'm going to evaluate it from 0 to 1. So it ends up being 1 squared over 2 minus 0 squared over 2. So it ends up being just integral 0 to 1 of x times 1/2 dx. Then we can integrate again, and we end up with, let's see here, I'll have 1/2 times x squared over 2 evaluated from 0 to 1. Well, that ends up being 1 plugged in, so I get 1 squared over 2 minus 0 squared over 2. That's just another 1/2, so I get 1/2 times 1/2, 1/4. So all this work we did looks really complicated. You thought maybe double integrals are going to be a whole lot more difficult than single integrals. But no, you kind of just do a single integral over and over again. The integration part actually isn't the hard part about multivariable calculus, multiple integrals. It's actually coming up with the bounds is the really hard part. And that's going to be what most people, struggle with. That's what I struggled with when I took this course. How do I come up with these bounds? And so we'll do some examples on how to come up with bounds in more interesting areas that aren't just squares or rectangles. What do you do when the base has some weird shape? It's not just a rectangle. Here's a more complex 2D integral. So we want to do integration over this triangular region. So we have, it's a triangle here, 0, 0, x is 2, y is 0, and then x is 2, y is 3. All right. And then let's start with this dx dy integral. So I tend to start from the outside. So I think, okay, what's the minimum value of y? What's the maximum value of y? Because we need numbers in these to evaluate the integral. All right, so I look and I say, okay, well, the minimum value of y is 0, right? Y equals 0, that's the bottom of the triangle. And then the maximum value of y is equal to 3. That's at the top of the triangle. So think, okay, well, we're supposed to go from 0 to 3. Now here's the next bit. So if you look at x, you might think, okay, well, x goes from x equals 0 to x equals 2. You might think, well, what if I just put 0, this is wrong, by the way, 0 and 2 there? Well, that's not quite right, because this describes a rectangle that is 3 high and 2 wide. And so you're adding in this extra triangle right here. And you can't do that. So it's not 0, 2. Well, okay, well, if it's not 0, 2, how are we supposed to do this? Well, here's the fun part. You can actually have variables in these bounds. All right? So now we have to think, okay, how do I do this if I have variables? Well, okay, let's try and figure this out. So if I'm looking at x, and I'm at a certain value of y, all right, so let's say I'm at y equals 0, right there. All right, well then x goes from this point to that point. All right, it goes from 0 to 2. All right, well, what if y is, let's see if I get this right here. What if y is equal to 1? Well, if y equals 1, then x is going to go from this point to that point. All right? All right, well, what if y equals 2? Well, if y equals 2, x is going to start here. It's going to go all the way to here. And then if y is equal to 3, well, x kind of goes just from 2 to 2. It's a little dot. So somehow we have to encode, we have to put into these bounds that where x goes from is actually dependent on the y value being integrated on the outside. All right, so the idea then is, okay, we're going to make an equation for this line. All right, so let's take a look here. Let's use, I think it's not that bad. So this line goes through the origin, and I think I have it here. So y equals the slope. We went 2 over and 3 up, so then that's 3/2 x. All right, let's just double check that works. When x is 0, y is 0, and yeah, that's one of the points. When x is 2, right, y is 3, and right, 3 divided by 2 times 2, that'll give me a 3. So yeah, this looks like the equation of the line. Well, all right, so now I have something. I know the value of y. I can know the minimum value of x and the maximum value of x. So the maximum value of x, actually, we do know. That is going to be 2. No matter what value y is, we go from this line to 2. So the top bound is 2. But the bottom bound is this line. And now here's one thing. We can't put 3/2 x here, because if we do that, we have essentially x in the integral bounds, and we have dx as an integration variable. It's also kind of doesn't mean anything. We were supposed to pick the range of x based on what the value of y is. So rather, we're going to have a function of y here in terms of x. Right? We want to know where x starts based on what y is. All right. So then to do that, we're just going to rearrange this. If I multiply both sides by 2/3, I'm going to get x is equal to 2/3 y. All right, and let's see how that goes. So 2/3 y. All right, so now let's take a look. Let's make sure it works. So if y is 0, we're going to go from 2/3 times 0 to 2. So 0 to 2. When y is 0, we're going from 0 to 2. If y is 1, then x is going to go from 1 times 2/3, so 2/3 to 2. Yeah, I'm pretty sure this point here is 2/3. And x will go from 2/3 all the way to 2. If y is 2, then we're going to have x going from 2/3 times 2, so 4/3 to 2. And so this point here, that's 4/3. And yeah, we do. We go from 4/3 up to x equals 2. So this is how you describe the integral for a region that isn't a rectangle. The bounds are going to have variables in them. And you're allowed to use the variables that are in exterior integrals. So right, we have this 2/3 y dy. And if we integrate with respect to x in this thing, we'll get some x's. We'll pop it in, we'll get 2/3 y plugged in, and then we'll have a function of y when we're done. All right, so this is how you describe it. Well, okay, there's more than one way to do this integral, though. So what if I had done integral. I still have my function f of x, y. We're not going to evaluate them, we just want to set them up. And instead of dx dy, I want dy dx. Now for this bit, we can't just switch the integrals, because here we'd end up with 0 to 2. Well, that's okay, you know, but on the exterior we have 2/3 y to 2. We can't have variables in the outer bounds, because this thing is supposed to evaluate to a number when we're done. We just can't flip them. We actually have to redo the bounds. All right, so let me draw the same picture again. So, close enough. Let's see, 2, 0, 2, 3. All right, we're still doing that region in the middle, but now we're essentially picking x first, and then we're going to figure out the range of y based on what x is. All right, so now this one, the range on x is 0 to 2. So I'm going to put 0 to 2 right here. All right, which is not 0 to 3, right? We couldn't just flip them. Okay, now based on what x is, I need to find the range in y. All right, so then here, well, okay, if x is equal to 2, then y goes from 0 to 3. If x is equal to 1, then y goes from 0 to, what is that? 2 thirds? 3 halves, I think. Yeah. If x equals 0, then y goes from 0 to 0. All right, so it looks like what happens is, no matter where we start in x, we go from y equals 0 up to y equals the function of that line, y equals 3 half x. So here this is going to be a 0. Y always starts at 0 no matter what x is, but then depending on what x is, it's going to go to different heights, and it's going to be 3 halves x. Let me write that a little bigger here. And now let's just double check it. Right, so if x is equal to 0, then y will go from 0 to 3 halves times 0, so 0 to 0. X is 0, y goes from, there's really no arrow there, 0 to 0. If x is 1, then y will go from 0, so starts at 0, and will go up to 3 halves times 1, right, because x was 1. And yeah, that does look right. If x is 1, y starts at 0 and goes up to 3 halves. If x is equal to 2, then y, according to this bound, y is going to go from 0 up to 3 halves times 2. So 3 halves times 2, that's 3. So y goes from 0 to 3 when x is 2. And yeah, that does look right. If x is 2, y will go from 0 up to 3. So not only were we not just able to flip these, they actually changed quite a bit. So right, this one was 0 to 3, this one's 0 to 2, somewhat similar. But this one used to be 2 thirds on the bottom y to 2, and this one is 0 to 3 halves x. So I kind of did a flip there. But right, this is the hard part of the course, actually. Hard part of multiple integrals. It's setting up the bounds. And let's do a few more examples just to make sure we got the hang of it. Next 2D integral is another triangle. This one, though, is going to have a little surprise. All right? So if I want to integrate over this region in a 2D integral, the first thing I need to do is I need to figure out the equations of these lines. All right, so let's start with this one here. All right, so I know the y-intercept is 5. So this is going to be y equals, let's see the slope. So if I go over 4 units, it goes down 3 units. So it sounds like it has a negative 1/2 slope, and then x, and then plus 5. All right, let me just double check that here. So if x is 0, then y will equal 0 plus 5. Yeah, that sounds right, so that's 0, 5. If x is equal to 4, then we're going to get negative 1/2 times 4, so that ends up being negative 2. Negative 2 plus 5 is positive 3, and yeah, y equals 3 when x is 4. So it looks like I did that correctly. Next one is going to be, okay, y equals, so this one I go 4 units over and I go up from 1 to 3, so that's going to be a positive 1/2 slope, and then my y-intercept is 1, so plus 1. All right, let me just double check that works. If x is 0, y is 1, yeah, that works. If x is 4, then 2 plus 3, y is 3, yes, that works. Okay, so I got those equations right. And then let's go ahead and do a double integral. So we're going to set up integral. We're just worried about setting it up right now. We're not going to worry about doing the integration. And let's do dy dx first. All right. Okay. So if I look at the y, so I'll start at the interior integral bounds this time. If I look at y, what I'm going to do is I've already picked x on the outside, so if I'm at x is 0, I go from this line up to that line. Sorry, that wasn't a straight line. And I just do that over and over again. So then my lower bound should be this line equation right here. So it's 1/2 x plus 1. That's my lower bound. Then my upper bound is the top equation, which is negative 1/2 x plus 5. Okay. And then for my bounds on x, then that's just 0 to 4. Right? That's the entire triangle there. So 0 to 4. All right, well, that wasn't so bad. But what if I change it a little? What if instead of doing dy dx, I want to do dx dy? All right, so let's go ahead and see what happens with that. So I'm going to redraw my triangle, not quite the same. Something like that. Okay, so integral. I still have my f of x comma y. Now I want to do dx dy. All right, so in that case, I need to figure out based on what y is, I need to find the bounds on x. And here we'll have a little hiccup. So if I start here, I've picked my y value. So x goes from here to here, here to here, here to here, here to here, here to here. But then something weird happens. So this whole time I've been going from x equals 0 to x equals this line. But then I get to 3 for y, and now I start going from x equals 0 to this other line. And so I have this sudden change, this abrupt change in my bound. I'm always going from 0, but I don't always go to the same line on the right. So what ends up happening here is actually we're going to have two integrals. So first I'm going to rewrite these as x as a function of y. If I do that, all right, so if I move, let's see, the y minus 5 multiplied by negative 2, I'll get negative 2y plus 10. Let me just check I did that right. So 4, 3, right, yeah. Okay, if y is 3, then I get negative 2 times 3, and that's negative 6. Negative 6 plus 10 is positive 4. Okay, it looks like I did that right. If y is 5, then x should be 0. Negative 2 times 5 plus 10. Yeah, that's 0. So it looks like I inverted this line correctly. Then here, let's do that again. All right, so if I subtract the 1 and multiply by 2, I think I'll get x equals 2y minus 2. Let me just double check that's working. If y is 1, x should be 0. Yeah, that looks right. 2 times 1 minus 2, x is 0. If y is 3, x should be 4. So 2 times 3, 6. 6 minus 2 is 4. Okay, it looks like I inverted that line equation correctly. But right, I've got one part where I'm going from 0 to this line, and another where I'm going from 0 to this other line. So what ends up happening is you have to have another set of double integrals. There's really no way around it if you want to do this order of integration. So dx dy again. So from y going from 0 to 3, sorry, 1 to 3, I have a certain behavior. And then y going from 3 to 5, I'm going to have a different behavior for the x bounds. For the x bounds from 0 to 3, we start at x equals 0, and we're going to go to x equals 2y minus 2. X equals 0 to x equals 2y minus 2. Then for the second integral, if y is between 3 and 5, x is going to go from 0 to negative 2y plus 10. And that's all the setup. So this is to just demonstrate that yes, depending on the region, you can end up having to do more than one integral, because you have these abrupt changes in the bounds. But it also illustrates that sometimes there's a better way to iterate a region than the alternatives. So right, we could have done dy dx, we could have done dx dy. Maybe this integral is pretty hard, maybe evaluating is hard. We're not doing quite double the work here, but we are doing more work here than we are here. And so if you can, when you're doing your homework or you're on an exam, most of the time it's easier to do one integral instead of two, or one double integral instead of two double integrals. So try to keep that in mind when you're going to make your bounds and you're going to pick what order of integration you're going to use, because it will change how much work you have potentially to do to actually solve that problem. 2D integrals again in rectangular coordinates. So this time we're just told to integrate this region between y equals x squared, y equals x, and 0 less than or equal to y less than or equal to 4. Okay, so first we want to try and draw a picture. So x, y. So we got y equals x. Well, I can draw that one for sure. And we'll have a 4 here. And now I've got y equals x squared. So here you have to be careful when you're drawing this to get it right. And I want to put in my numbers here. So in here, these two functions will cross when x equals 1. So at this point. So I'm going to kind of exaggerate it to make it easier, but it's a parabola, and it goes up. And so they both cross at that point. So there's this little region right here we have to worry about, and there's this other region up here we have to worry about. And I'm going to cap it off because it's between y equals 0 and y equals 4. So we've got that. All right, so let's go ahead and look at our double integral then. And let's say arbitrary function f of x comma y. And now we want to know d what? Which order is easier? Okay, well what if we did dx, or dy dx? Yeah. If we do dy dx, then we pick an x value, then we do dy in the interior. So, x is equal to this value, they go from 0 to 0. X is equal to this value, they go from the bottom of the parabola to the top of the line there. X is equal to 1, y goes from 1 to 1. X is equal to, let's say 2 or something, I'm not sure. Then it's going to go from the line up to the parabola. But here we do have a problem. So right about there, you actually have a split. So if you do dy dx as the integration order, then you'll actually have to end up making 3 integrals. One for this little region, one for this little region, and then one for this little region. Because your bounds are changing all the time. So we'll do that in a bit actually, but let's just start with the easier one. So let's do dx dy. All right. So then dx dy, okay, well, what are these two things in between? If I'm always doing dx going this way, well, it looks like I'm between the line and the parabola. So I have to change the parabola to be in terms of a function of y instead of x. So right, y equals x squared. That's the same as x equals square root of y. You got to remember, it's plus or minus. We got to pick the right one. And I think I have. So in that case, right, we go from x equals this line up to x equals this. So it looks like we should do from y equals x to, x equals y to x equals the square root of y. That's not going to be right. So just keep that in mind. This is a mistake people commonly make. But let's find out why it's not right. All right, so x goes from there to there, there to there, then there to there, there to there. And so y is going from 0 to 4. All right, now let's double check. So we go from value of y to value of square root of y. And that one works out for a while. So we do have these little arrows going the correct way in this little section. Let me just expand it. Right, they're going this way. But when we get up to here, they actually end up going the opposite way. We end up going from the line backwards to the parabola. And that's no good. So same reason you can't do kind of decreasing x in 2D coordinates is the same one as in single variable calculus. It ends up actually making the area you're integrating negative. So you're not allowed to do that. So we actually do need two double integrals to integrate both these regions. So it's not going to be 0 to 4 y squared of y. It's going to be 0 to 1. That'll handle this region, and it's going, from the line to the parabola. But then we need to add on integral 1 to 4 integral. We have to flip these. So it's going to be square root of y to y. And it's the same f of x function, xy function, and it's the same dx dy order. All right, so just keep that in mind. Even though it's going, between the same two functions the whole time, we do have to split it correctly to make sure we're always increasing, going in the direction of increasing x on the bounds. Right, so we always want it to be like that in both regions. All right, well, now for some fun. What if we do the triple integral? And we do, we're going to do dy dx. Let's just see how that works out. F of x comma y dy dx plus integral f of x comma y dy dx plus integral f of x comma y dy dx. Let's see what that has to be. So in that one, if we're picking dx last, then we have to go, this way. So it's going from y equals x squared up to y equals x. Yep, and then x is going here. It's from 0 to 1. Oof, sorry about that. Oh, sorry, x squared, excuse me. All right, but then we get to here, and so let me do that. So, right, the one we've started with, we went like this. But now we have part of the region, so I'm going to do my line, and I've got my parabola, and y equals 4. And so now we have to do from the line up to the parabola. Oh, shoot, sorry. This is squared on the bottom. Right, sorry about that. Okay, now we have to go from the line up to the parabola. But what's the bounds on y? When does this thing stop? Well, so I didn't draw it very well to scale here, but if this is y equals x squared and y equals 4, then that's going to be, 2. So not the best scaling on my part, but that's 2, 4. So that's going to go from 1 to 2. And then we're actually going to transition. So that was kind of this piece. But then we have to do this piece here. So then we have this one, and this one, and this one. So in this case, we're going to go from the line y equals x to y equals 4. And that's going to be from 2 to 4. So y equals x to y equals 4. Did I get that right? Yeah. So, that was fun. But yeah, so sometimes you do keep in mind which way you're going. You always have to go in always have to go in increasing x and increasing y on the bounds. And even if you have the functions that do cross each other, you have to keep in mind that when they cross, they flip which one you're going to go from which one.